So I like to continue then. The fuzzy logic is a new kind of logic when we can use intermediate truth values, not just excluding truth values 0 and false. We could have some overlap between the truth and the false values. The person who invented that was Lotfi Zadek. He worked for Berkeley, and one of the first introduction was in this topic in 1965. And at the beginning it was rejected, as usually happens, no inventions. But finally, later on, it became some kind of marketing slogan because it was a sign of efficiency, to make something efficient. Wash machine, for example, or controllers. And I like to tell you briefly in the following some minutes, how does it work. As I mentioned at the beginning of the last class, it changed my world how to see things around me when I understand first this fuzzy method. Our thinking usually based on traditional logic. For example, binary logic, especially if we are in a computer field. But another example, for example, the jury system. If somebody is doing something bad, the judge had to decide guilty or not. He cannot tell partially guilty, even though the situation is usually that. He has some different circumstances what he can consider, but the final decision had to make binary, guilty or not. And if he's guilty, the person will have a punishment. If he's not guilty, he can walk free home. So we need to make an artificial decision to make it binary, even the situation is not binary. The idea of what Zadek introduced to define variables with intermediate truth values. The way to handle it, one way to easily handle it, make this kind of data set, telling that if the value is 10, the truth value is 0.1. Not 100%, not totally 1, just 0.1. And then, if the value is 40, the truth value is 0.2. A good example, for example, if we are talking about speed, car speed. If somebody is driving 200 kilometers per hour in a city, we can consider that this is a very fast car. It's a very fast. If he is driving just 20 kilometers per hour, it is a very slow. And if we need to tell it is fast the way how that person is driving, we can check the value and we can say if it is 10 kilometers per hour, it is just not very smart, not very fast. It is just smart, 10% or 1%. And he is driving 200 kilometers per hour, it is 100% fast. So this kind of categories are always relative. We need to see where we are. And then we need to make this kind of data set. And how we can represent this, for example, on this function, like this. For example, this is the speed of the car. And then above 230 kilometers per hour in a city, it is a very fast move. Under that, it's not so. Depends on the situation. And how can we get this red line? To test it, to get data and opinions, for example. Based on the opinions, we can draw this conclusion. What is the percentage of the truth value? If we would ask someone, the person was driving on a highway 240 kilometers per hour, almost everybody would say it was a very fast car. It is not allowed to do that. But the person was driving only 90 kilometers per hour, we could tell, oh, it is not too bad. It is not too fast, but not too slow, something intermediate. So this kind of function, what we can see, he named it membership function, meaning that what is the value of this given situation, what member of the truth value and a false value. And each of the variables can be represented not just a single value 0 or 1, rather a graph, or rather a data set, telling that what given situation, what given value belongs to what truth value. Based on these steps, based on these variables, this is the basic procedure to design fuzzy systems. First, we need to define the input and output variables. If you want to make a system what has inputs, we have some expected outputs or decisions. We need to define the variables. This is the first thing. If we define the variables, then we need to define the truth values for those variables. Let me tell you a very simple example. If you need to wash your clothes using a wash machine, it's a very simple procedure. You will collect your clothes, put it into the wash machine, and push the button on it, and it will wash it for you. And some minutes later, we'll take it out and dry it. But as you know, it's a little more complicated, because if you want to make an efficient method, if you want to do it efficiently, you need to consider many things in it. For example, how many clothes you have, what is the weight of the clothes what you want to wash. If you have only one underwear, it is not worth to put it into the whole machine, start with a huge amount of water and detergent and something like that. So one factor is how much is what is the weight of the clothes. The second decision what you need to make, how much water you are going to supply for this washing. It can be a minimum, it can be maximum, there is some intermediate value between that. The third question is, what should be the temperature of the water what you are putting there? Very cold or very warm or intermediate, you need to decide. Fourth element, how much detergent you are going to put in it. If the clothes is dirty, probably you put more. If it is not so dirty, not so much. And something like this. For example, in this very simple example, we have only four variables. The amount of clothes, amount of water, temperature of the water, detergent. Of course, it is good to know it is very dirty or not. If it is very dirty because you was working on it in an oily situation, it will be a fifth factor, it is very dirty. And then you need to decide how many times you are going to wash it, and when you washed it, how many times you're going to rinse it to clean up the detergent from it, and something like this. You need to collect this kind of elements. And then if you have these elements, you need to learn what is what. For how much is the how much. For example, if you have a kilo, it is much or not. The reason why? Because if you would watch a person, somebody who is expert at washing clothes efficiently, using the minimum amount of water, minimum amount of energy, minimum amount of detergent, and a fastest washing time, if somebody can do it, because we humans are very smart to do this kind of simple tasks efficiently, we can ask the person, why are you doing that? And the person would tell you, since it is not much, it is just a small amount of clothes. It is not very dirty. Because of that, I will give just a little detergent for that, and I don't heat the water too high because it is not needed, and I will rinse it 2 times because this is my experience to do it in this amount of water, this amount of clothes. And this kind of rules are some kind of relative rules. It is not a fixed thing. You can ask how much is how much. How much is a 1 kilo, how much is a liter, how much is the temperature, something like that. To be able to handle it with a computer, you need to define the variables. You need to define the fuzzy variables. What is the function of the much or few? Clear? If you have a chance to do that, you can describe all of the variables using these fuzzy membership functions. And then the next step is we need to collect rules. Unfortunately, human rules what we are using, usually not so accurate. For example, this example, what I just told you, the person who is washing the clothes can tell it is not so dirty and not so heavy, that's why I'm not using too much water. I'm not heating that too much. And what is the not too much? So we need to have this kind of rules, so-called fuzzy rules. And if we have these fuzzy rules and the fuzzy data, we need to figure out how to make conclusions from that, what kind of inference we are going to use for that. The problem is the following: all of the truths are partially true, because all of the inputs are somehow true, partially true. So we need to have some kind of method to select the final answer, because finally the machine, the dumb machine who uses electricity and water, will run certain period of time, and after that it will switch off. The operation of the machine will be not fuzzy, it will be crisp. It will turn on a given minute, it will turn off in another given minute. And we use a given amount of water for that, and we need to put a given amount of detergent in it to be able to wash properly. Clear? So, if this is the situation, then we can test the system, and if it is optimal, we can say it's great, we have it. But if not, we need to tune it. We need to play around with these membership functions. The rules could be the same, but to change what do we mean it is too much or not too much, or too heat, too much, too warm or not too warm. That's something like that. If you have a chance to do that, we can adjust the system, and finally, when we adjust it using some kind of simulator, for example, MATLAB has a good fuzzy simulator in it, and if you play around with the simulator, we can build in this controller into the regular microprocessor controller. The same controller what was already built into the wash machine, but instead of using just a binary logic, it will use this fuzzy logic. And as you understand, the key element here to utilize the human knowledge. We can utilize the person's knowledge who was washing in the previous years continuously. Because there is a way to build in his or her perfect knowledge, even though it is fuzzy. Because I know how to do it. If it is very dirty, it's a huge amount of clothes in it. Of course, I wash it several times, heat up the water very much, about 70 degrees Celsius, something like that, or 60 degrees, and put a lot of detergent in it, because a lot of detergent, I need to rinse it several times at the end, something like that. And if we want to optimize it, somehow put it into the machine, this is what we need to do. Somehow figure out how to represent the fuzzy values, how to represent the fuzzy rules, and then to make how to make inference from that, how to make conclusions, and somehow adjust it. Good news, we can do it. And because of this knowledge what we have, as I mentioned, it became a marketing slogan to write on a device it is fuzzy controlled. Because without fuzzy control, it wasn't so efficient. As I refer to the very first picture what I showed at the beginning of the class, if we have a knowledge line, one end is the rule-based, another end is the data-based. This fuzzy approach is in the middle, because we can utilize the human knowledge, but is not so accurate, but still efficient, and we can build it into the computer. So this is, for example, one of the examples for the linguistic variables. For example, talking about the height, human height. If I am, let's say, 180 some centimeters tall, I can ask, am I a tall person? I ask you, and I ask you, I ask you, and I ask you, and you can tell yes or not, or what percentage you think. I ask you, for example, if I'm 200 centimeters tall, you would say I'm a tall person. If I'm 160, you would say not so tall. And you can tell how much it is. It is about approximately 60% tall and 30% not tall. I hope it makes sense. And based on this kind of survey, I can somehow summarize this survey, and we'll have this graph telling that, for example, 140 centimeters, like this here, in this point here, 140 centimeters, about this is the truth value. Projecting this here, almost 50% true and 50% false. 170, it is a little more true and less false. 200, 100% true. So this is the membership function. And for each of the variables, we need to define this fuzzy membership function. This is the first key element. We can do the same thing for the speed, or with a cold and a warm, for any variables what we are using. And based on this membership function, we can represent any variables in this new sense, because there are some intermediate truth values, intermediate false values. And this is how the fuzzy looks like. It is black in the middle, or dark in the middle, and white at the end, and somehow fuzzy inside, at the edges. The edges are not crisp, rather some intermediate values. This is one of the typical curve for curve, for example, the Gaussian distribution. Anything in nature who is influenced by many, many factors can usually show this kind of interesting distribution, meaning that most of the data falls within this range, and then some part of it falls in this range, and a very small part falls in this range. This is called the standard deviation, this area around the average. Many variables can be represented like this. For example, one of the key elements these days that I think what I learned from my children, the fear of missing out. Many people, this is the guiding method for many people, many of us, to do something because we are missing out. But it is not binary also, not like this, rather like this here, like a Gaussian distribution. In the middle, it is 100%, at the edges are less and less. Good example for this fuzzy situation is the life. For example, if this is the lifespan for a human, this is the birthday, this is when the person dies. And in the middle, somewhere, if somebody is 60 or 50 or 40, we can tell the person is alive. Usually, this is in a good health. If somebody is just 1 day old, it is questioned if the person is healthy or not. We cannot test it yet. It will turn out. The same thing happens at the other end. If somebody is 95, his mobility is not so good usually, his ears are not so good usually, so his vitality, the way how we can handle things, it is not 100% anymore. It is much less. And sometimes there is a definite time here, definite situation, but we name it death, when a person dies. But it is an artificial limit, because when a person dies, some parts still be alive. For example, the skin is still alive, the nails are still alive for a longer period of time. So there is some intermediate value between that. But we artificially truncate it. If somebody cannot breathe, we can tell the person is dead. Or his brain function, it is not active, it draws a straight line in an EEG, we can tell the person is dead, and then based on this decision, the person can become a self-donor. So the life usually produces this membership functions, and if we need to utilize it in a system, we need to find the numerical representation of it. And this is the key first. And then, if we have this data set, it can be as a result of the statistics. So for example, this is the small value, this is the truth value of the small, this is the truth value of the high, this is the truth value of the medium. But the question how to feed it into the regular computer, because these days we have digital computers. Very simple answer for this. We can do like this here. We can tell this is the turning point, this is another turning point, but instead of using this smooth graph like this here, the data set, we can decide this is the 100% true, this is some kind of linear area between that, and this is 100% false. The same thing applies for the high value, and the same thing applies for the medium value too. Instead of using the data set, we use just this turning point to represent the membership function. It is very efficient and very easy to handle. Usually, if we need to use variables, we cannot have 100 different categories. We can have small, medium, or high, or we can use something like this: small, small, medium, 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 high, high, something like that. Because our rule base in our head, it is not good enough to handle much more complicated situations. For example, when you learn to drive a car, when you sit in a car and the driver, the teacher next to you, what he says, okay, go ahead, go more, go follow. And if you are too close to the other car, you say, oh, push the brake. More, more, and more, and more. What is the more? And what is less? Something like that. We can handle the situation, but we cannot handle 100 different categories, just maybe 6 or maybe 5 or something like that. These are the typical situations here, the medium, small, medium, something like that. And instead of handling these smooth curves, we are using these truncated ones. because we need to store in a computer only these points, these so-called turning points. This one, that one, so on. And if the value falls between that value, this is the truth value. For example, this is the speed, for example, here, and we are here, let's say in this point. I project it here, and I project it, and it says this given value gives us what? Truth value. Clear? So this is the first step to make fuzzy variables, like this way. The second step is somehow to understand how we can make conclusions of this fuzzy variables. As I showed you before, if we have a binary logic, we can define the logical function between them, the AND and OR and NOR and XOR, so on. The same thing applies for the fuzzy too. For example, if I have only two variables, A and B here, this is the four different kind of combination what we have. Both of them can be 0, both of them can be 1, or 1, 0, 0, 1. Based on these four combinations, we can decide what is the AND connection between those, or what is the OR connection between those. But the problem, these variables are not binary values, rather like this, rather these membership functions. For example, this is the membership function for the A, let's say. A, see, this is the membership function for the A. This is the membership function for the B. If you want to decide what is the AND connection between A and B, we need to handle these two input variables, two input membership functions. And the way to do that, this is the AND connection, meaning that if this is the A, this is the B, when it is connected together in an AND connection, at the beginning, the 0 is stronger than the high value, because it needs to act together. If the A is almost 100% 1, the B is 100% 0, the 0 is stronger. So this is the result. This is the result of the A and B. Because here the small values are stronger than the big values. And if we reach this intermediate point here, and going further up in the variables, we can see this smaller one is stronger than the big ones. And then it comes down like this here. Please raise your hand if you understand this. Thank you very much. If not, please check it, because it will be on a test. I will ask you to draw. I will give you some input variables and ask you to make an AND connection or connection or something like that. If you don't understand, you cannot answer it. To have the OR, this is the two input variables, A and B. This is the membership function for the A and B. And if I need to connect with these two variables using the OR function or logical function, either this one or the other one, if the one is almost true, it is 100% true. And it's coming down because it is coming down and other is increasing till the point when the other will be stronger, other will be more true. And that's why it goes like this here. Question again. Raise your hand if you understand this. Thank you, good. So, it is just an example to show you how to define logical functions using fuzzy logic. If we have input variables using membership functions, then we have a way to represent the logic functions in it, the connection between those. Based on this very simple way to do that, we can build inference mechanisms, some kind of way to conclude, to draw results from the input data, based on fuzzy rules. This is the block diagram of the fuzzy system. The way how it works, we need to have transformation between the input variables. Usually the input variables are crisp. It's the data. We can measure it. We can measure the amount of clothes what we are washing. We can measure the amount of water what we are using. Or the detergent, we can measure it. It is a data. But to tell what this data means, we need to define this kind of numeric fuzzy transformation. And the membership function is doing that. So we need to have the membership functions. We need to decide this is the first step. This is the input membership functions, and somehow we need to transfer the input data to fuzzy data. Clear? And if you have like this here, then we need to have a fuzzy rule base. Question how we can get the fuzzy rule base? Asking from the experts. Because in many areas there are experts. One example that I like to tell you here, once I had a fortune to sit or test the Burj Khalifa tower in Dubai. It's a fantastic feeling. If you have a chance to visit, please do it. The reason I actually not I want to proud it is not an achievement. I was just lucky to get there once. But what was a great interest for me, I was standing in the elevator, and it went up to the 120, approximately 120 levels. What do you think? How long it take us to take up to the 120 levels of the building? 1. It was 1 minute. We stepped into the elevator, they closed the door, and 1 minute later we went out. The guy who was sitting in it, I don't think he was the one who controlled it. He was just controlling how many persons can come into the elevator. But the way how it was handled, probably obvious. When we started, the acceleration should be very high, because otherwise we will fall down on the floor. So when it started, it went very slowly. But when we are traveling in a 20th level or 30th level, the speeding up of this elevator was probably very much. In the middle, in the 50th level of the building, it was extremely fast. But when we are approaching to the top level, it had to be slowed down very much, because otherwise we will jump when we arrive to the top. And instead of feeling that, it was no any sensation to feel that, because of this properly fuzzy control. And it was fantastic. It was very good. So to do this, we need to have this rule base, using the expert knowledge how to do it properly. And a good elevator operator could do it efficiently, but he or she would be very tired after a long day. And finally, when we reach this point here, we have an output. We have some kind of conclusion what to do. The problem is again here, these are the fuzzy rules also, fuzzy data. We need to do exactly what to do. We need to figure out what is the action, what we need to do. So we need to translate back the fuzzy data to numerical data. We have 2 translations, one here, and then doing this fuzzy interference in the middle, and then we will have some crisp output. And this is a good example for the big group of problems what we can solve. For example, where we want to handle, just another one, I'd like to tell you one other example, where we want to handle music, stored music. Of course, we can use the regular backlight, the regular disk to store it. But it is not so efficient. It can be great to use it, but it is not so efficient. If we want to carry huge amount of data with us, huge amount of music, we need to do it digitally. But to be able to do that, this is the goal, to carry a lot of music with us, or have it with us. Then we need to have a transformation, digital transformation at the beginning. The analog signal had to transform to digital. Store it digital, at the end we need to retrieve it and convert it back to analog, because this is what we can enjoy. So this kind of transformation is a very typical situation in technology, in IT, for some purpose, for some different purpose. And this is the purpose here, to have a fuzzy rule base, what we can utilize. Use the expert knowledge. This is the main goal. To be able to use the expert knowledge, we need to sacrifice this work, the transformation to fuzzy, and from fuzzy to other one. The way how it works, for example, these are the input variables, A and B. These are the outputs, A and B. And the rule for connecting these 2 variables, it is not a crisp value, it is also some kind of fuzzy value, something like this. For example, if A is true, then we will do capital A. If the B is true, something like that, then we will do the capital B. This is the 2 human rule. But as you see, it is overlapping. There is some overlap between that, because partially if we have this value here, this given value, it is partially A, partially B. And the partial representation, partial truth value can be measured here, on these values here. Clear? The problem, because of this, we need to have a method how to evaluate these different rules, because all of them is acting usually together. Not only one rule, several rules acting together. So we need to somehow select what we want to execute, what we want to use. So if this is the numerical value, this from here to here is the truth value of the A, this is the truth value of the B, like this here. And both of the rules is active. This rule is active, that rule is active, because the input falls into that range. And we need to do something. That's why you need to have some kind of answer selection mechanism to decide what is the answer. Because I cannot say rule A and rule B is okay, because both of them is okay partially. So we need to decide what to do. And there are many methods. One of the methods of the many is that select the big ones, select the big rule, what is the larger one, and then, since the goal is to have some crisp output, what we need to do, for example, how much water we need to put into the wash machine, we need to get the biggest rule, and then the so-called singleton method is called singleton method, find the middle point of it, this middle point. And this is the output. Because the whole range is there, but we need to decide what is the action finally. We can say the intermediate, the middle point of it. This is the one method to do that. There could be another method, so-called the averaging method. If both of the rules are active, both of the rules what we need to use can be applied, then we need to calculate the average point of the big rule, the other rule, and then if these are the values, these are those belonging values, then we can use, for example, the weighted average. We can do like this here. Multiply the area of this rule set with this value and make an average of it. Based on this kind of answer selection methods, finally, we have a tool how to combine the different rules what is acting in the same time. And if you have a tool for that, we can utilize the human knowledge, we can feed in fuzzy data based on the experience what we have, what we collect, and we test the system. And if we test it, and it is proper, optimal, close to optimal as a human person would do, we can replace the human. And then we can build it into a controller, and the controller will do the job. So something like this. And there are famous names I just like to mention. We don't need to learn the method, but if interested, you can do. For example, Mamdani was one of the famous Japanese person. The Tagai Suganov was another method to do that. How to combine the different rules what acting together. And then, if we have these methods, then we can have a crisp output. Going back to the data, the block diagram, input data. Input data are usually crisp. No, not that one. Sorry for this terrible thing. So the input data is usually crisp. The output data is usually crisp because we need to tell how much water, how much heat, how much detergent. But in between those, there are these transformations. Crisp to fuzzy, rule-based, and fuzzy to crisp. I hope it makes sense to you. Something like this. Now I think it makes sense to you what I projected at the beginning of this class. These are the steps: definition of input variables, collecting fuzzy rules, selection inference mechanism, and fine-tune the system. And if we have a fine-tuned and well-tested system, we can build it into the controller and we can have it as a functional device. These are those main features for the fuzzy system. I think it makes sense to you. It interfaces the mathematics and the computer science using human rules. It should be based on the fuzzy set theory. The set theory, just I showed a very simple example how to make a AND connection and how to make the OR connection, how to make the NOR connection, something like that. And then based on this basic consideration, we can have a set of math for handling that. We can use the human words to describe the system. That is a main advantage. Instead of having rules, fixed rules, binary rules, or equations, we can have human experts who can tell these fuzzy human words. Too much water, too much speed, or something like that. And we have an answer, what is the too much? And then we can incorporate it into the technology, and it can be applied for many, many situations. Not always. There are some certain critics against fuzzy, because in a fast-changing situation, it is not good. Because fast situations, person is not good for it. But it is very good if the person can do it, and we want to replace the person. Because we don't want to pay a salary for him or her, or we want to make it reliable, or we make it not to tire after a certain amount of time, something like this. Finally, this is the last thing what I'd like to ask you. To understand the situation, please answer these questions. And I hope I supplied enough resource to be able to answer those. Why we need the truth values, and so on. So this is what I wanted to show you today, and I have 5 more minutes, but I won't start the next presentation. Next time, week from now, I have 2 topics to cover. One is what we learn from nature using different sensors, what kind of rules we are using to sense the world, and those rules can be applied for technology. And the second part will be to next week talk about the trends in AI, the very fascinating trends, and I'd like to show you some elements of the state of the art. This is what I have for next week, and 2 weeks from now will be the test. Would you please prepare? And so, if you need, I can have a consultation next week. If you have questions, happy to answer. There's a consultation time after this class. If you have questions, happy to answer it. Okay? Thank you very much. Thank you.